Meta's internal data for their ranking engineering agent shows a 5-fold increase in engineering output for their ads models, alongside a 2-fold increase in average model accuracy compared to previous baselines. These clean metrics exist on top of a brutal operating environment. Optimizing them involves distributed multi-week pipelines, where nodes fail, configurations diverge, and metrics regress. Engineering a useful agent for this environment involves an architectural redesign that allows the system to survive days of idle wait time without timing out or breaking its context. Scaling AI across complex production environments relies on moving towards state-persistent, asynchronous systems that operate over weeks. In Meta's ads architecture, retrieval systems filter millions of ads into thousands of candidates. Massive models then score them within a strict 100-millisecond latency bound. Optimizing this requires coordinated steps, formulating hypotheses, modifying code, and waiting weeks for training runs to finish. Standard React loop coding agents fail in this workflow. They are designed for rapid observation and action, which causes them to time out or idle while waiting for heavy infrastructure jobs to complete. Standard synchronous AI architectures that burn tokens to continuously check job status are incompatible with heavy ML infrastructure workloads. Meta addressed this with the Hibernate-and-Wake primitive. In this execution loop, the agent launches a training job and immediately stops at a barrier representing a multi-day cluster wait. Instead of idling, the agent shuts itself down entirely to conserve resources. Before powering down, the system executes state serialization. It compresses its current plan, tool traces, and hierarchical working memory, writing them directly to a persistent database. While the agent sleeps, an orchestration system monitors the cluster, waiting for the job to reach a terminal state. Once finished, the watcher triggers a wake event. The system pulls the serialized memory and injects the data to resume the workflow. Decoupling the wait states from the token generation process underpins long-horizon autonomy. The agent can orchestrate workflows spanning several weeks without continuously consuming compute. To generate viable experiments in a massive codebase, the system uses a secondary knowledge loop to feed the planner. An internal ML research agent proposes novel optimization paths, searching for gains that escape local dead ends. Simultaneously, a historical insights database provides rigid data on past successes and failures, grounding the search in historical reality. Synthesizing these streams ensures diversity with grounding. Because the hypothesis generation is anchored by historical data, the agent avoids proposing changes that would spike inference costs or trigger known infrastructure errors. Before the execution loop begins, the agent formulates an exploration strategy using a pre-execution planning phase. The search space follows a 3-part progression. Validation tests individual hypotheses, combination merges promising candidates, and exploitation optimizes the survivors to maximize results. Before starting the first validation test, the agent calculates an estimated GPU compute cost for the entire plan. The workflow stops here. A human engineer must authorize the budget before the agent accesses the server infrastructure. Once approved, the agent handles routine failures independently, using internal runbooks to auto-triage infrastructure issues like out-of-memory errors without manual intervention. Production AI requires these upfront constraints.
RIA operates within strict compute limits and human approval checkpoints, prioritizing governance over uninhibited exploration. The initial metrics, 5-fold output and 2-fold accuracy, must be weighed against several points of missing data in the report. The engineering output metric specifically tracks the throughput of launch proposals across models, rather than the full cycle of realized production wins. Meta does not provide a breakdown of the volume of compute used for dead ends, failed runs, or discarded hypotheses. Furthermore, reported accuracy improvements rely on offline evaluations. In ad systems, these gains often regress in a live environment if they increase inference costs. While RIA scales the volume of concurrent experiment pipelines, the current data does not confirm an increase in raw compute efficiency per unit of success. The achievement of RIA rests on the scaffolding of system orchestration rather than a sudden leap in foundational model reasoning. Persistent state memory and tool integration shift the primary constraint of machine learning optimization from an execution bottleneck to a governance bottleneck. Engineering teams should audit their own workflows for long-wait infrastructure tasks that are ready for this kind of asynchronous delegation. A frontier AI agent is defined by its engineered capacity to hibernate, wake up, and persist long after the human engineer has gone to sleep.